Hello brainers, my name is Jace and welcome to the Big Brain Busters. So in this video I am going to take you through body fluid compartments, then we are going to look at units of measurement, and lastly we're going to look at body fluid indicators. Then as usual I have added some practice questions at the end of this video to see whether you've understood, so I'd advise you to attempt the questions and see whether you've actually understood. With that being said, let's proceed. Okay, so we are going to start with body compositions. So as you can see from my table here, these are different kind of body compositions that are made that our bodies are actually made up of. So as you can see, we are made up of proteins, fat, mineral, and water. And these are different body weight percentages. So protein, we are actually made up of 18% of protein and protein related substances. Then our body fat or adipose tissue is actually 15%. Then mineral, we are made up of 7% of mineral salts, and as you can see, total body water in our body is actually 60%. So this actually shows us that a large proportion of our body is actually made up of water. Okay, 60% of our entire body weight is actually what? Water. Okay, and this data that I've presented here is in relation to a 70 kg grown up adult, and that's a man. Okay, let's proceed. So continuing with our body compositions, my next diagram here actually shows different the body compositions at different stages of life. So as you can see, we had already articulated on our previous diagram about different body compositions. So now you find that when we are newborn babies or neonates, we are composed of 80%. So 80% of our uh, total body weight is actually made up of water. Then as we grow up, as you can see here, the total body water is actually decreasing in percentage. So when you reach in men, as you can see, an adult man of about 70 kg weight, you find that they're actually composed of 60% of water. Their total body weight is 60% water. Then in an adult woman, you find that women actually have more adipose tissue, or in short, they have more fat than men. So for them, you find that the amount of water is actually lesser than that of men. So the amount of water for them, it's 55% of their total body weight. Then as we grow up, both men and women, you find that as we grow old, um, we our body is actually filled with more fat. Then the amount of water actually reduces. So you find that the total body weight, 50%, 50 to 55% is actually made up of water. Okay, so let's proceed. Okay, so now let's look at our main focus of the day, which is body fluid compartments. So as we have already articulated previously, to say for a normal adult male, we will use that as a reference. Normal adult male in this video, who is about 70 kg, you find that they are composed of 60%. The total body 60% of their total body weight is actually made up of what? Of water. Okay, so the total body water of a normal adult of 70 kg mass is actually about 42 liters. Okay, so here, as you can see, the total body water of is actually on average 60% of the total body weight. Then that's in a 70 kg man, or in general we generalize it to 50%, 50% to 70% of all individuals. Okay, then when you calculate 60% of 70 kg is actually giving you 42 liters. Okay, when you punch on your calculator, it will give you 42 liters when you do the math. Then the total body water is actually divided into two main compartments. This water is actually divided into intracellular fluid and extracellular fluid. So intracellular fluid is just simply fluid inside the cells, okay, which is ICF. And this intracellular fluid is actually 40% of the 60% of total body water. Okay, or in short, it is 2/3 of the total body water. So when you calculate 2/3 of 42 liters, it should give you 28 liters. Or in short, 40% of 42 liters, it should give you what? 28%. Okay, then extracellular fluid, which is the internal environment of cells, is actually, which is the ECF, is actually 20% of 60%. So as you can see here, which makes sense in the math, when you add 40 plus 20 is actually 60. Okay, or in short, extracellular fluid is actually 1/3 of total body water. And when you do the math, 1/3 of 42 liters, it will actually give you what? 14 liters. Then when you calculate 28 liters plus 14 liters, it will give you what? 42 liters. Okay, let's proceed. So now, extracellular fluid, that's where we end. Then the main deal is on the intracellular fluid, we end there. Then extracellular fluid, that's where the main deal is, because it is subdivided into two other compartments. So it is divided into plasma fluid and interstitial fluid. Plasma fluid is the fluid in our blood, okay, the liquid part of blood, which is plasma fluid, and it is simply 25% of extracellular fluid. So when you calculate 25% of 14 liters, it should give you 3.5 liters. Okay, it's not 25% of total body water, but 25% of extracellular fluid. Okay, so in this 20%, now there is 25% of plasma fluid. Then interstitial fluid. Interstitial fluid is the fluid that bathes our cells. In short, it is the fluid in between our cells. Okay, yeah, it bathes our cells, right? And it is actually composed of 75% of extracellular fluid. So when you calculate 75% of 14 liters, it should give you 10.5 liters. And when you add 3.5 plus 10.5, it gives you what? 14 liters. Okay, then there is another type of extracellular fluid, which is not calculated as a fraction of extracellular fluid, but it is calculated as a fraction of total body water. But it is a type of extracellular fluid, and that compartment is known as transcellular fluid. So transcellular fluid, it's a very, very small proportion of a body fluid compartment. It is composed of 2.5% of total body water. So for this one, you don't calculate it as a fraction of extracellular fluid, but you calculate it as a fraction of what? Of total body water, and it is composed of 2.5% of total body water. And when you calculate 2.5% of 42 liters, it will give you what? It will give you 1.05 liters. Okay, then this transcellular fluid, as small as of a small proportion as it is composed of other sub compartments. And these sub compartments are, you have CSF. So CSF is just simply cerebrospinal fluid. So the fluid that is found in our in our brain and the spinal cord, right? It cushions our brain and our spinal cord. Then you have intraocular fluid in our eyes, interpleural fluid in our lungs. It prevents friction between the lungs and the ribs, right? Then we have the peritoneal fluid, in our peritoneum, PA in the abdomen. Then we have our synovial fluid in the joints and digestive secretions, such as saliva. Saliva is a digestive secretion. Then we have other secretions in the in the stomach and everywhere else. Yeah, so this is the total body fluid compartment. So these are the divisions. I hope you've gotten something out of this. Let's proceed. Okay, so as you can see here, this is something, again, just to show the body fluid compartments, another diagram. So the total body water, as you can see, is divided into two main compartments, intracellular and extracellular. Then the intracellular fluid, okay, intracellular fluid, which we said that intracellular fluid is composed of 40% of the total body water, okay, and of which we mentioned that total body water is actually 60% of what? Of total body weight. Then the extracellular fluid compartment is actually 20% of the total body water. Then this 20%, now this extracellular fluid is divided further into two sub compartments, which is interstitial fluid and plasma fluid. Now you should know that between intracellular fluid and extracellular fluid there is a cell membrane. So that's where intracellular fluid and interstitial fluid, that it is separated by a cell membrane, as you can see here. So we have this cell membrane here that separates our intracellular fluid from our interstitial fluid, okay, the fluid that bathes our cells. Then between interstitial fluid and plasma fluid there is another barrier, which is a capillary wall. So this capillary wall is very much impermeable. This capillary wall is very much impermeable to what? To substances moving in and out. Okay, so as you can see, so this interstitial fluid is actually as a result of what? Of plasma fluid actually entering into this compartment. Okay, so this capillary wall here, when plasma fluid, when colloid pressure is actually high, so there is what we call colloid pressure, okay, in the capillaries, that actually allows movement of fluids from plasma to the tissues. Okay, so when that colloid pressure is actually high, you find that fluid will start moving. Okay, fluid will start moving, substances in short, they'll start moving from plasma to what? Into the interstitial fluid, in that direction. Okay, so one thing why this capillary wall is very much impermeable to different substances, this is because in plasma here you have different proteins. It is mainly composed of proteins. Okay, so these proteins have got the characteristic of keeping water to themselves. Okay, they attract water to themselves, making it um, very hard for water to actually move, to actually move into another compartment. All right, so let's proceed. Okay, so let's take a look at some of the clinical applications of body fluid compartments. In short, what can go wrong when these body fluid compartments are not maintained. So there is a condition known as edema, which is just simply abnormal fluid accumulation in body tissues. So it is mainly caused by increased capillary permeability. So remember that on the previous slide we are talking about the capillary wall, right? Which is very impermeable to different substances. So when that capillary wall has actually increased in its permeability, you find that there will be fluid leakage into tissues, okay, from plasma into tissues. So that is what we call edema. So you find that it presents with swelling of different body parts, or due to accumulation of fluid in body tissues. So an example that we can give is this one. So as you can see here, there is this normal leg without edema, then there is this swollen leg here. So for you to know that this is actually edema, you actually try to compress or perhaps put pressure on that swollen part, then you find that there will be this pitting. Okay, there will be like a small hole that will be formed, this a small pit. Okay, then another type of edema is known as ascites. So ascites is just simply accumulation of peritoneal fluid in the peritoneum. Okay, so this is the abdomen, there is increase in peritoneal fluid. Then another type of edema is simply what? Is simply pleural effusion. So pleural effusion is just simply increase in pleural fluid here in the pleura. So there is the pleura in the lungs. Okay, then due to abnormal drainage of lymphatic fluid, you find that there is accumulation of what is pleural fluid, then that will lead to pleural effusion. Okay, so let's look at some units of measurement. So you should know that we have three main units of measurement that we use to express amount of solids. So the first one is simply a mole, which is just simply a substance of a known molecular structure, and we know that 1 mole of a substance is actually equal to this Avogadro's constant, which is 6.23 times 10 to the power 23 what? Molecules. Okay, then another next unit of measurement is known as equivalent, which is the amount of charged solutes in a solution. So when you get a solute and dissolve it in a solution, you find that it will dissociate, and when it dissociates, it will produce what? Ions or charged particles. So the amount of charged particles in that solution is what we term as what? Equivalent. So and it is calculated using this formula. Equivalent of a solution is equals to number of moles of that solute multiplied by what? Multiplied by the valency of the solute. So here is an example. Calculate the equivalence of potassium chloride and calcium chloride when dissolved in a solution. So here I will only use the example for potassium chloride. So you find that potassium chloride, KCl, when it dissolves in a solution, it will dissociate into what? Into potassium ions and what? And chloride ions. And potassium has got a valency of 1, chloride has got a valency of 1. So we say that to find the equivalence of potassium chloride, we will say we will multiply the number of moles, of which here this is 1 mole of potassium. So 1 mole of potassium multiplied by the valency, which is 1, so meaning that we'll have 1 equivalent of potassium. Then again for chloride ion as well, we have 1 mole of chloride ion. Then this 1 mole of chloride ion multiplied by 1 or by 1, which is its valency, you find that we also have what? 1 equivalent of what? Of chloride ion. So go ahead and try out for calcium chloride and see if you've understood. Then you should drop the answer in the comment box. Then I will reply whether it is correct or wrong. Okay, let's proceed. Then the next unit of measurement is simply osmos. So osmos refer to the number of impermeable particles dissolved in a solution regardless of the charge. So the amount of impermeable particles dissolved in a solution regardless of the charge is known as an osmo, right? So those were units of measurement. So now when we relate those units of measurement to concentrations, you find that in this case now, concentrations, we'll find that if we are using moles, we'll say mole per liter. If we're using equivalents, we'll say equivalents per liter. And if we are using osmos, we'll say osmos per liter. Now, how about in biological organisms? So you find that these solutes in biological organisms, they actually exist in low amounts. So in short, we calculate them in milli amounts. So what do we mean? So we calculate them in terms of millimoles instead of moles. We calculate them in terms of milli equivalents and milli osmos. Okay, then in terms of concentrations, we calculate them in what? Millimoles per liter, milli equivalents per liter, and milli osmos per liter, in that simple way. Okay, so now let's look at the last terms, which is osmolarity and osmolality. Okay, so what is osmolarity? Osmolarity is the number of osmos per liter of a solution. So the number of osmos, remember an osmo, we say that the amount of substance that is dissolved in a solution, right? That is an osmo. So now the number of osmos per liter of a solution, so the number of osmos that are dissolved in 1 liter of a solution. So that's what we mean by osmolarity. Then how about an osmolality? It's the number of osmos per kilogram of a solvent. So in 1 kg of a solvent, the number of osmos that are dissolved in there, that's what we are defined as osmolality. Then therefore osmolarity is affected by volume of various solutes in the solution and the temperature, while osmolality is not, because osmolality is affected by the what? By the mass. Okay, I hope that makes sense. Okay, so now let's look at some body fluid indicators. So measurement of body fluid volumes can actually be used using indicators. So depending on the specific body fluid compartment that you want to measure, you use indicators, you inject indicators in there, then those indicators will spread, and then you are able to measure your body fluid compartment volume. Okay, so to measure total body water, you use 3 main indicators. So this is tritium oxide, this is deuterium oxide, then this is antipyrine. Okay, so these are the 3 main ones that are used to measure total body water. Then to measure extracellular fluid, so to measure extracellular fluid, you can use inulin, which is the most common one. You can use thiosulfate, you can use sucrose, you can use iothalamate, and you can use this isotope of sodium. Okay, so what makes these indicators so special to measure extracellular fluid? So this is because these are composed of large molecules, and remember that extracellular fluid is separated from intracellular fluid via a cell membrane, so that these large molecules cannot cross the cell membrane. That's what makes it so special. So meaning, since they cannot cross the cell membrane rather, meaning that they cannot enter into the intracellular fluid compartment, making them suitable to measure extracellular fluid, because they will only spread in plasma and interstitial fluid. Then to measure intracellular fluid, you cannot measure it using indicators, but rather you can use instead you can use the formula, because remember that total body water is just simply the sum of intracellular fluid and extracellular fluid. So meaning that if you have calculated your total body water and you have calculated your extracellular fluid compartment, meaning that you can just subtract total body water minus extracellular fluid, then meaning that you have found what? Your intracellular fluid. I hope that makes sense. Then to measure plasma volume only, okay, excluding the entire extracellular fluid compartment, just to measure plasma volume only, you can use albumin. Okay, you can use Evans blue dye, which is the most common one. It is also known as T1824. Okay, then to measure blood volume, blood volume can actually be calculated as plasma volume divided by 1 minus hematocrit. Okay, so hematocrit is just simply the amount of red blood cells in that collection of your when you collect your blood sample in the test tube. So the amount of red blood cells in your total blood volume, in your total blood, you actually get your hematocrit, and hematocrit is actually also known as packed cell volume. Okay, then to measure interstitial fluid as well, you can measure it or calculate it by simply saying that extracellular fluid volume minus plasma volume, then you have calculated your interstitial fluid. Okay, let's proceed. So what are some of the characteristics of these body fluid indicators? So these body fluid indicators require specific characteristics that should make them suitable to actually be used as the indicators. So the first one is that okay, so this is just a formula that you can use when applying body fluid indicators to measure these body fluid compartments. Okay, we are going to in another video we're going to look at calculations on how you can calculate these volumes and everything. So now right now let's focus on characteristics of body fluid indicators. So the first one is that the indicator should be non-toxic, meaning that it should not intoxicate you when you have been injected with a body fluid indicator. Okay, I mean, imagine you're being injected an indicator, and then it causes harm to your body, meaning that that won't be good. So it should be non-toxic. Then the next one is that it must mix evenly throughout the compartment being measured. So meaning that it should be specific. When you only want to measure total body water, it should measure total body water. And if you only want to measure ECF, it should only measure what? ECF. The next one is that it must not have any effect of its own on water and other substance distribution in the body. It should not have any effect. Okay, it should not react, in short, anywhere. Okay, then the next thing is it must be easy to measure. So that body fluid indicator, it should be easy to measure. So if you say, okay, I'm going to inject about, maybe, let me say, let's say 4 liters. Anyway, that's too much. Maybe let's say I'm going to measure 2 liters, like something like that. Yeah, so it should be easy to measure. Then the fifth one is it must be unchanged by the body during mixing period, or amount change should be known. So this is where this formula has come in. Okay, because when you inject a body fluid indicator into your body, you find that at times that fluid indicator can actually react with certain chemicals in your body. So the amount that has reacted, or the amount that has been excreted, should actually be known. Okay, or else it should it should be unchanged by the body. It should not react with the body, remember. But if it reacts with the body, and if there is any metabolic reaction in the body, that amount that has been metabolized should be known, should be of known what amount, so that why, so that we are able to account for it when calculating. Okay, we should subtract the amount that has been excreted. So this is where this formula comes in. I hope all this makes sense. Okay, so these are some of the practice questions that I've put at the end here. Please try to answer them, and try to drop comments in the comment box so that I may see whether you are able to answer, or maybe there is anywhere where I need to, give assistance. All right. So this is where we end our video. Don't forget to like, share, and subscribe, which are our 3 magic words. All right, brain nerds. This is where we end. Shalom, shalom. Okay.